Hello and welcome to Chapter 11.3 from Stevens' Introduction to Statistics, the Think and Do book. In this we are going to do ANOVA tests, and this is just an introduction, mostly because we can't really do these by hand. Hand calculations are almost impossible to do with an ANOVA test. So it's an introduction, and a little more emphasis than usual will be placed on output from software, because it's really the only way to do an ANOVA test. So in this chapter you'll see more results from software and how to interpret these results. So when you get done with this chapter, you should be able to conduct an ANOVA test. It's just some of the details and the nuts and bolts might be a little fuzzy. Okay, so way back in chapter 9.2 we tested for a difference in means between two samples, right, or two populations. In this section, we test for a difference in means between more than two samples, right, 3 or more. We conduct what is known as a one-way analysis of variance, ANOVA. So the ANOVA stands for Analysis of Variance, right? Popular test. So we are testing for a difference in means between 3 or more samples. And what we could do, we could just do a collection of individual two-sample comparisons. But the problem is that if we have many more than 3 samples, that results in an awful lot of two-sample tests, right? An awful lot of them. And when you start doing a whole lot of these tests, it does increase the likelihood of getting a significant difference just due to random variation. So this way we're able to check for a difference in means between more than 2 populations and not run the same risk of observing a significant difference that was due to random variation. It is called one way because the differences in samples are defined by one variable, such as the treatment to a certain situation. In this test, it's funny, we actually compare variances between samples and within samples to see if there's a difference in means. Right, so we're actually analyzing variances to detect a difference in means. We never actually compare the sample means. And that's kind of strange, but it's effective. And we'll see how it's done. We'll see sort of why this works in the one example that we can do by hand. The difficulties with this test, the calculations are nearly impossible to do by hand, even with a good calculator. There are some very simplified examples where it can be done, but they're oversimplified. And then finding critical values, tables developed for the sake of finding critical values. There's a lot of variables that go into the critical value, so the tables are sometimes numerous and complex. The terminology in a full ANOVA test in most statistics books is much greater than what we're going to see here, and it is pretty complex. You will see one example completed by hand, and it is unrealistically simple. All software packages, all statistical software packages, will contain a routine to perform ANOVA tests. And they calculate the same values, but there are differences in output and terminology, especially terminology. But we'll get into the terminology so that whatever software package you're using, you'll be able to recognize the key players in the results. The requirements to conduct an ANOVA test: the distribution of all populations involved should be approximately normal. The variances of all populations should be about the same, unless the sample sizes are the same. The samples should be independent, not matched or paired. And if they're sampling, it should be a random sample. Right? So here's the notation. The test statistic is actually an F. It comes from the F distribution. And the way this thing is calculated is it compares the ratio of variance between groups with the variance within groups. Right? And this is called, in some software or in bigger books on the topic, this is called MS for mean squares. And it's a way of estimating the variance. Right? So you have the variance between groups and the variance within groups. and you calculate that ratio, and that gives you the F test statistic. The idea of between groups is also called treatment or factor, and I'll show you where that shows up a little later. And the variance within groups is also called the error, right? And the MS stands for mean square. It's a weighted mean of squared differences, so it's an estimate of the variance. DF is the degrees of freedom. There is one for the numerator, right, and one for the denominator. And that's what makes the table so difficult, is if you start creating tables for critical values, you have two different degrees of freedom going on, and you have different significance levels. So a table for critical values for the F distribution is usually a whole lot of tables with various degrees of freedom for the numerator, various degrees of freedom for the denominator, and various significance levels. So it's usually a lot of tables. And that's actually why we're not going to do it here. We'll let software do it for us. Alpha is, again, the significance level, and F sub alpha is the critical value of F for the given significance level, and the significance level is alpha. That's why there's a sub alpha there, right? It determines the rejection region, and the p-value is a measure of the extremeness of the test statistic. So let's take a look at this F distribution. It has a shape similar to the chi-square distribution in the sense that all of the F values are positive, and the shape actually depends on both degrees of freedom, the degrees of freedom for the numerator, the degrees of freedom for the denominator. So there's a lot of variations on this F distribution. It is not symmetric, it's skewed, and all the values are positive. All tests are right-tailed tests, and the p-value is the area under the curve to the right of your test statistic. That's the p-value of the test statistic. And the critical values, F sub alpha, determine the rejection region, right? Just like in the chi-squared, the critical value determines the rejection region, which is all values of F to the right of the critical value. P-values and critical values must be obtained with software. There is no single easy-to-use table. There is collections of tables that can be used, but even then, there's a chance that you won't see your degrees of freedom in there. So we're just going to let software do it, because software does it quick and easily. To do it by hand it's really quite brutal. So the process for an ANOVA test is just like the process for any other hypothesis test. We first start off, determine the null and alternate hypothesis, and the null hypothesis always looks like the mean from the first population is equal to the mean from the second is equal to the mean from the third, and so on. So the null hypothesis is that all population means are equal, and the alternate hypothesis is that at least one of the means is different from the others. Right? Then you calculate the test statistic and the p-value of the test statistic with software. Then you have to decide, do you reject or fail to reject the null hypothesis? There are two equivalent methods. There's the critical value method, where you reject the null hypothesis if the test statistic is larger than the critical value. And we're not actually going to focus on this method because we're using software which will just spit out the p-value. So that's always nice. So the p-value method is we are going to reject the null hypothesis if the p-value is smaller than alpha. And alpha, again, is the significance level. All right, so, and then as usual, you want to end with an understandable conclusion. If you reject the null hypothesis, there is sufficient evidence to conclude that the population means are not equal. And if you fail to reject the null hypothesis, there is not enough evidence to conclude that the population means are not equal. So in the first case, you make a pretty strong conclusion that one of these means, at least one of these means, is different from the others. If you fail to reject the null hypothesis, you haven't proven that all the means are equal. You just don't have enough evidence to suggest that they're not equal, right? So the two negatives does not quite equal a positive in this case. Okay, so I'm going to do one oversimplified example by hand, and it sort of shows you where this is going. So suppose we have 3 samples, all with 5 numbers, right? Our first sample, second sample, third sample. And if you calculate the mean of the first sample, it's 4. Calculate the mean of the second sample, it's 5. Calculate the mean of the third sample, it's 6. So these sample means are pretty close. And I've also calculated the sample standard, or not standard deviations, variances. So those are the sample variances. All right? And so the way we get the variance between groups, it's a type of variance, right? We're going to take the sample size, we're going to weight this variance, times the variance between means. So that's the variance here. So the average, the mean of those means is 5. So the variance is, x bar minus the mean squared plus the next x bar minus the mean squared plus the next x bar minus the mean squared, all over, that's n minus 1. Right? So that is just a sample variance multiplied by the sample size. So we get the variance between groups is 5. Right? And if you look at the variance within groups, all we're going to do in this case, because the sample sizes are all the same, we're just going to average the 3 variances. So we take 1 plus 2 plus 2.5 divided by 3. So the average of the variances in this case. And by the way, these formulas only work because these sample sizes are the same. When the sample sizes are different, the calculation for the variance between groups and within groups is much more complicated than this. But in this nice simple example, the calculations aren't so bad. So we get a variance within groups of 1.83. And so the test statistic is the ratio of these two. So it's variance between groups or the variance within groups. And what you see is you get a test statistic of 2.72. So not recognizing the scale, we don't know whether that's big or small. I can tell you it's small, but here's an example of a big one, right? So in case 2, we're going to have disparate means. So in case 1, these means were similar, 4, 5, and 6. They were pretty close to each other. In case 2, the means, sample mean for sample 1 is 4, sample 2 the mean is 5, but sample 3 the mean is 10. So that's much different than the other two, right? So if you calculate the variance between groups, so you take the 5, that's the sample size. So you're going to basically take the sample variance of these 3 numbers. And what happens is this 10 minus 5 squared gets pretty big, because this one's kind of large. And you divide by n minus 1, multiply by 5, and you get the variance between groups is 51.67. So notice that got bigger. The variance between groups got much bigger. And the variance within groups is actually still the same, because the variances did not change. Right, all I did was add 4 to every number here to get these numbers. So the variances remain the same for all 3 samples. But now the ratio, that variance between groups, much bigger, divided by the same variance within groups. And now I have a test statistic of 28.18. Right? So some observations. In case 1, the means were pretty close, and this caused the variance between groups to be small at 5. And that caused the test statistic to be fairly small at 2.72. In case 2, the means were not close, 4, 5, and 10. This caused the variance between groups to be large, right? That was the 51.67, and that caused the test statistic, F, to be large at 28.18. So notice the ratio, when the means were pretty close, the ratio of the first group was 2.72. When the means were not close, the ratio of the variances was very high. And this is the F value. So notice when the means were disparate, I get a very large F value. So we were able to detect differences in means by analyzing variances, and hence the name analysis of variance. You're actually looking for a difference in means, despite the word mean being completely absent from the title. The sample sizes were all the same. That made the hand calculations possible. Calculating the variance between and within groups is far more complicated than this procedure suggests when the sample sizes are different. And even so, when we got all done, we didn't have the critical values of f or the p-value of the test statistic, so we weren't able to say whether or not we were going to reject the null hypothesis. We will let software do this for us. Right? And so I'm going to demonstrate some output from Excel. Right? So we'll look at our oversimplified example that we did by hand, only we'll have Excel do it. And it's a really simple process. You just highlight the data and choose ANOVA test, right? And so when you do that with Excel, with that data with the similar means, I want to draw your attention to a few results from this output. MS, that's the mean squares. Those are the variances, right? Source of variance. So the variances are right here. Between groups came in 5, and within groups came at 1.833, just like we did with our hand calculations. And then we got a test statistic, which is the ratio of those two, under the F column. There's the test statistic, 2.72, carries out obviously more decimals than we did by hand. And then what it does produce that we weren't able to get is the p-value of the test statistic and the critical value of f. So here the p-value is 0.105. So that's the p-value is kind of large here. And the critical value, 3.885294, that's the critical value, and it depends on alpha. In this case, I believe I set alpha, the significance level, to 0.05. Right? So in any case, software gets us the p-value and the critical value. Actually, it gets us everything we need, right? So we have a fairly large p-value here. When we look at the case with the disparate means, and we did this by hand, we got the variance between groups is 51.67. Within groups is still small at 1.83. And the test statistic was 28.18. So the results from Excel, MS, that gives us our estimates on the variance, 51.67 or 6667. So these are our variances between groups and within groups. F is the ratio, matches what we did by hand. But this critical value, that's actually very small. That's 2.93 times 10 to the negative fifth. So that's actually 0.0000293. Right, so it's very small. So I have a very small p-value, so I'm likely to reject my null hypothesis that the means are all equal. And again, the critical value is the same at 3.885. But now notice the test statistic is deep in the rejection region. In the first example, the test statistic was not in the rejection region. Right? And so it's probably worth right now pointing a couple things out. These are the results from Excel. If you use other software, the names here might be different. Right? So this between groups, it might be called treatment. And let me put it over here. So the between groups might be called treatment or factor. So other software might have, instead of between groups, it might have treatment. And that's basically between the different treatments. It comes from a medical application of the ANOVA test. And this within groups will often be called the error. Right. So if you're not using Excel, and you're probably not, look for those words instead of between groups and within groups. Although I'm not certain, because there's so many, I think some of them do use between groups and within groups. I think Minitab might use the same terminology, but I could be wrong. Okay, some observations. The MS column gives the variance between groups and within groups. The F column gives the test statistic, and that's the ratio of the two variances. The p-value column gives us our p-value, as it should, right? So that's good. The F-crit column gives the critical value on F, but that depends on alpha, and is denoted F sub alpha in this section. right? And I should also point out that some software packages don't even bother giving you the critical value, right? Because that depends on, you have to choose a significance level. And so some software packages just give you the p-value because that is actually perfectly sufficient to get you through any hypothesis test. And now we can determine whether or not we reject the null hypothesis just by looking at the p-value. If the p-value is less than alpha, we reject the null hypothesis. If the p-value is greater than alpha, we fail to reject it, right? So we're going straight with the p-value method. And in examples here and in the worksheet and in the problems, I will actually give you the test statistic and the p-value. So almost all of the work is already done because it must be done with software. So let's take a look at an example. And this is where the sort of terminology started with. It started with medical applications. So we have a new drug for lowering cholesterol, and it was tested for its effectiveness on men with high cholesterol. Some men were given the new drug, some were given a placebo, and some no drug at all. 1 year later, a researcher randomly selects 10 men from each group and checks their cholesterol level. And the results are given in this table, the first table, right? And the second table displays the results from an ANOVA test. And so this is sufficient information, especially because you got this. This was nice, right? So if we conduct our test, the test that we're going to do is we're going to test the claim that there is a difference in mean cholesterol levels between treatment methods. That's why those between groups is often called treatment. It's between the treatments. And we're going to test this claim at the 0.01 significance level. So the null hypothesis is that all the means are equal, and the alternate is that at least one of the means is different from the others. So we calculate the test statistic and the p-value using software, and that's what I did here, right? So we're done. That step's extra easy in this particular presentation of ANOVA. So the conclusion regarding the null hypothesis, well, I look at the p-value, it's 0.0599. My significance level is 0.01. All right? So the p-value is bigger than the significance level, so we fail to reject the null hypothesis. So the conclusion goes like this: there is not enough evidence to conclude the population means are not equal. Again, we did not prove that they were equal, we just didn't have enough evidence to support the claim that they were unequal. Right? And again, the double negative does not actually imply a positive. Specifically, at the 0.01 significance level, there is not enough evidence to support the claim that there is a difference in mean cholesterol levels between the treatment methods for all men. Right? So that brings it back down to our specific problem of this cholesterol medication. Okay, does your conclusion change at the 0.05 significance level? Well, look, the p-value was equal to 0.0599. So the p-value is actually still bigger than the significance level, but not by much. So nothing does change. Does your conclusion change at the 0.10 significance level? Certainly. Switches all together because the p-value now is smaller than the significance level. Right? And so we would reject the null hypothesis, and at the 0.10 significance level, there is sufficient evidence to conclude that the population means are not equal. So if I'm a little riskier with my statements, I would come out and say, yes, I reject the null hypothesis. There is reason to believe these population means are not equal. Specifically at the 0.10 significance level, the data supports the claim that there is a difference in mean cholesterol levels between the treatment groups. There's a note worth observing. This test doesn't tell us which one is greater or less than the others. I mean, we can make a speculation here because we have the sample means. If we do come to the conclusion that there is a difference in means, that they're not all the same, you could say, well, it certainly looks like the no drug group is a lot higher than the other two. But in order to really make a claim about one being greater than the other, you have to go back and do individual t-tests between the two groups. And again, that's kind of risky because if you do too many of those, you increase your probability of a type 1 error. Okay, and we actually did do a single comparison between the no drug and drug, and we did get a p-value of 0.0119. And we concluded at the 0.05 significance level that the drug population did in fact have a lower mean than the no drug population. Right. But that was at the 0.05. We wouldn't be able to support that claim at the 0.01. But that's back in Chapter 2 when we did a specific comparison between two samples. Alright, so here's the your turn problem. Again, these are easy because you get the results of the ANOVA test right there. So a student obtains the GPAs from a sample of 12 freshmen, 10 sophomores, 8 juniors, and 11 seniors. And the results are summarized in this table. The second table gives the ANOVA results, and we will assume that the GPAs from the populations of each class have a distribution that is approximately normal. That way we can use this process, right? That's one of the requirements. So we're going to conduct the test, and we're going to test the claim that the mean GPAs for all students in each class are not equal. We'll test this claim at the 0.05 significance level. So we want to determine the null and alternate hypothesis. Well, we have 4 different possible means, so the null is always that they are all equal. The alternate is that at least one of them is different from the others. Right? It doesn't tell us which ones are different from which ones, but that all it's saying is that they're not all equal. What is the test statistic and the p-value? You're in luck there because I gave that information to you that I obtained with software. I did not calculate that by hand. And the test statistic is 3.078. But more importantly, the p-value is 0.0393. That gives us an indication of how extreme this f-value is. So specifically, at the 0.05 significance level, our p-value is smaller than the significance level. So we're going to reject the null hypothesis. So we're rejecting the hypothesis that they are all equal. So what that means, there is sufficient evidence to conclude that the population means are not equal. Specifically, the data supports the claim that the mean GPAs for all students in each class are not equal. And again, this doesn't tell us which ones were higher or which ones were lower, only that they are not equal. Right. So in that sense, the ANOVA test falls a little bit short. But if you do have a lot of different populations, you might be able to take this ANOVA test and then do just a few 2-sample tests and really make some stronger statements. So our p-value is equal to 0.0393. And at the 0.05 significance level, we rejected the null hypothesis. What about at the 0.10 significance level? Well, the p-value is still smaller than the significance level. So again, there's no change. We still reject the null hypothesis. Does the conclusion change at the 0.01 significance level? It sure does, because now the p-value, 0.0393, is now bigger than the significance level. I'm a little more conservative with my statements, and so now the p-value is too big, and we failed to reject the null hypothesis. And so, again, that doesn't mean we proved that all the means were the same. There is just not sufficient evidence to conclude that the population means are not equal. Right? So that wraps up this introduction to ANOVA. And, I made it pretty easy because in all of the problems, in the worksheet and in the homework, I'll give you the ANOVA results. And what that means for you is that the p-value is already given. So conducting a hypothesis test is really just a matter of taking the given p-value and comparing it to your significance level. And that'll tell you immediately whether or not you reject the null hypothesis. So this chapter was made a little bit easier than you would probably see in most stats books. But that's because I feel that the ANOVA test really should be done with software and not by hand. So that wraps up Chapter 11, except for the summary worksheet. So I will see you at the summary worksheet, and it actually wraps up all the material in this book. This is the last section of new material. So it has been a pleasure, and if you tune in, I will see you for the presentation on the summary worksheet. If not, good luck with the course. Take care.